Okay, math or computer science 140 students, this is Dr. Sweeney. This is one of these supplemental lectures that we've got here for computation. And I want to highlight a couple of things. What we're going to do right now is we're going to be looking at algorithms, and we're going to start talking a little bit about how do we count the number of computations that we have in an algorithm, because that's really primarily what we're concerned with inside of this computation section. That's the big piece that we've got here in computation. So what I'm going to do here is I'm actually going to kind of define a couple of things, and then we're going to look at some pseudocode, and hopefully you've done the reading, and so you can go in and look at, you've gotten some introduction to the pseudocode. And then once we do the pseudocode, we'll kind of like talk a little bit about how do we count the number of operations. So we're going to start here, and we're going to start out with this if and the if-else statement. And so we want to remember we're working in logic, right? Because computers work on logic. And so we have, if we start out with the if statement is going to define first a condition for us. So like, for example, if x equals, right, 5. Okay, so if x equals 5, and so we're going to assess whether or not this is true or not. Okay, and then afterwards, immediately afterwards, we don't actually write inside of pseudocode. We're not going to put a then. We're just going to say what it is. If x equals 5, we'll assign, let's say, for example, we'll say y equals 7. Okay. So we're going to get some data, and as we pull the data in, what's going to happen is that this computer program is going to check if the x value that we're pulling in is actually equal to 5, and if it is, it's going to assign then y equal to 7. Okay? And there it is. What happens if x doesn't equal 5? Okay? If x does not equal 5, nothing happens. Right? Remember, this is a conditional statement. And since it's a conditional statement, if we get the hypothesis false, it doesn't matter what happens with whether or not the other part is false or not. We just don't do anything with it at all. Okay? So let's say, for example, if sky equals blue, then, okay, turn on the computer. Or the computer equals to on. All right? Basically, that's the idea. Is this an assignment of numbers? Is this really an algorithm? No, it's not, but that's kind of the idea. And actually, we wouldn't even have a then. If sky equals blue, computer equals on. How about that? And we'll change it up to that, and that's your if statement. We also, though, have an if-else statement. So an if-else statement is a little bit different. So we've got if-else here, okay? And if-else actually looks like this. It says if, and let's say, for example, if x equals 5, y equals 7. Now remember, in the straight if statement, nothing happens if x doesn't equal 5. Well, what we're going to do in the if-else is we're going to then say, okay, else y equals 0. And then that actually assigns 0 to everything where x is not equal to 5. Okay, and that's our if-else statement. And that's kind of like how we think about the if statements when we look at algorithms. These are very basic if statements in algorithms. Now let's look at the for loop. And when we talk about the for loop is our first kind of important, like the if and the if-else are actually very important for algorithms. The for loop, though, is going to be really important for assessing the number of computations that we have inside of any given algorithm. All right, so what we're going to do is we're going to sit here and we're going to say, okay, well, what happens with the for loop? The for loop actually tells me for what values in my data set I'm actually going to go in and assess an if or an if-else statement. And so inside of any algorithm, we're going to start out with a data set, and basically this data set is going to be the a sub i's. Okay, this is the data set. It's a sequence of numbers. It doesn't have to necessarily be in any kind of order. All right, it has its own order. We actually oftentimes are going to have functions that will go in and order the data set, but this is the data sequence. And you'll notice that these i's, okay, the I, that's the index. And so when we're looking at an algorithm, our i's are going to correspond to values in certain places inside of the index. So like, for example, if our a sub i's are our inputs, okay, and oftentimes you'll see it look like that. It's inputs are something of the nature of, let's say we have 1, 5, -3, 8, 12, -4, no, -5, and 7, okay? Now, a sub 1 is going to equal 1. A sub 2 is 5. A sub 3 is -3. These are locations in space, or locations inside of our our sequence, all right, that correspond to particular values that are inside of the data set. So when I see something like this, for I equals 3 to 7, I equals 3 to 7, I'm looking at, here's a sub 3, a sub 4, a sub 5, a sub 6, a sub 7. And so those are the 5 values that I'm looking at. I'm not actually going to run this for loop for anything other than I 3 to 7. Okay? And so those are going to be the values that I'm going to be working with. What this is going to do is this is going to tell me what values in my data set am I going to do whatever if-else statement that I'm going to do here inside of my for statement. Okay? And we'll notice for I equal 3 to 7, I'm going to have 1, 2, 3, 4, 5. I got five statements there, so it's 7 minus 3, okay, which equals 4 plus 1, which equals 5. And those are going to be the values that I'm going to be running that for. And so that's actually going to come in really handy because that's going to be kind of like one of the ways that we're going to go through and count how many times I'm going to do a for loop. Okay, so that for loop, and we'll talk more about this in a second when we do more pseudocode, that for loop, we're going to actually count up the number of operations that I'm going to be doing, or the number of times I'm going to do everything in the if statement, and it's going to end up being based upon this for loop. Oftentimes we'll see something like this: for I equals 1 to n minus 1. Right? Basically, like say for example, if I want to actually like do a comparison between values 1 to n minus 1, and then the last one is a sub n, that's the last value inside of my sequence, right? Okay, my last value, then that's actually going to be, like we might leave that one off. Notice what we do here is we're going to do n minus 1, so that equals n minus 2, and then we have to add a plus 1, which is equal to n minus 1, because what this is it's called inclusive. So the number of times that we're actually going to run this loop, the for loop that we have here, is actually going to be n minus 1 minus 1, okay, plus 1, right? Take the end statement minus the beginning statement and then add an additional 1, right? Oftentimes it's pretty easy. If you start at 1, that's going to be the number. Like in this case, n minus 1 is going to be the number of operations that we're actually going to do inside of the for loop. Now the while loop is another important piece that we're going to be using here inside of our discrete structures course. We're going to be very basic with the while loop, but basically what the while loop is going to do is it's actually going to tell us a place to stop instead of at the end of whatever sequence that we're looking at. So the for loop is oftentimes going to go through the entirety of the sequence, which if you think about it is actually kind of a problem. It's a problem because like you got to do it for every single value. What if we hit whatever number that we want, or we hit whatever characteristic or quality or condition that we want right at the beginning? Then what we want to do is we actually want to stop. I don't want to go through the entire set because that's just going to take up time. So the while loop is a much better choice there. Okay, so what we may see is we may see something like this: a while, and we'll have a while, and then we're going to have some kind of condition, all right? And this condition, let's say for example, while a sub I less than 5, right? Say imagine that we have an unordered sequence while a sub I is less than 5. So all we're going to do is we're going to go up until that value equals 5. You can imagine a data set in which we don't have any value, okay, that is in fact less than 5, so we don't have to run this while loop at all, okay? Or you could also imagine a data set in which every value actually happens to be 5 or bigger, and then you actually have to go through the entirety of the data set. Oftentimes what ends up happening is it's a little bit more tricky than that, or not tricky, but a little bit more elegant than that. We don't actually have to go through the entirety of whatever condition that we have, okay? So to give you an example, let's imagine that I have I, so we have an example, I have I is equal to 1, okay? And I've got some kind of sequence here, and that's going to end up being my assignment, and I've got while a sub I does not equal x and I less than n. So this condition is saying, all right, I'm going to assign a value for x. Let's say, for example, that x equals 7, okay? While a sub I does not equal x and I is less than 7, or I is less than n, then I'm going to do something. And this one actually has it, we're going to increment. I goes to I plus 1. Okay, so I'm just going to go on to the next value. So let's imagine I have a data set and this is 3, 7, 10. In this case, and then we have an end while, by the way. All right, so here's my data set, my set of inputs. I'm looking for x equal to 7. I'm going to start out at I equals 1, and then I'm going to actually go in and compare each and every time. Now, n here, n equals 3, okay? And so what's going to happen now is I'm going to go in and I'm going to say, okay, well, a sub I not equal to x, okay? So I'll start and I'll check out, and a sub 1 is equal to 3. A sub 1, 3 does not equal 7, because that's what x is supposed to be. And 1 is less than 3, so we're going to increment, right? I is now going to go up to 1 plus 1, which equals 2. And so that's now our new value. So I go in, I'm going to do this again. I've got a sub 2 now. A sub 2 is equal to 7. That does equal 7. So now I get to exit the while. End the while loop, okay? So I exit the while loop. And you can see that in this case, super handy to be able to exit the while loop because I don't have to go through the entirety of the list, okay? Now, here's the thing about while loops. We're going to really actually focus in on something called worst case time complexity. And when we talk about worst case time complexity, oftentimes the number of operations that we get for a while loop is basically the same in the worst case as it is in the what we call the best case for these loops. So if that's the case, what we've got to do is we've got to recognize that oftentimes when we're counting computations, and we'll talk about that more in a bit, the while loop and the for loop actually look very, very similar in terms of just their overall counts. So let's look at this piece of pseudocode, okay? And let's imagine I've got product, and we're going to set that, we're going to assign it to equal 1, and we're going to have count equal 5. So while count greater than 0, product is going to equal product times count, count equals count minus 2, and then we're going to end while, okay? So I've got product is 1, count equals 5, while count greater than 0, product equals product times count, count equals count minus 2, and then we'll end the while. So we'll start out, and what we'll notice is we're going to first check our condition, okay? We'll first check our condition. And for count greater than 0, what I've got here is I've got, I notice that count is equal to 5, so I'm actually going to run my while because count's greater than 0. Product is going to equal product times count. So product, notice, is 1, count is 5. So product, my new value after my first step, is going to equal 1 times 5, which equals 5. Okay? So that's my new product. My count now is going to equal, and count was 5, 5 minus 2, and that equals 3. Okay? Now, the next thing I'm going to do is I'm now going to check, and I'm going to say, okay, count is greater than 0. Well, totally count is greater than 0. It's 3. So since I have 3 as my count, right? So step 1 here, step 2, 3 is my count. It's greater than 0. Check the condition. Product is going to equal product times count. Okay? So product will equal 5 times 3, which equals 15. And then count is going to equal 3 minus 2, because it's count minus 2. Previous count was 3. 3 minus 2, and that equals 1. I now check my condition. Count is greater than 0 because it's 1. So now I have a third step. So now product is going to equal 15 times 1, because that's product times count. And count is now going to decrement by 2, so it's going to be 1 minus 2, which equals negative 1. Okay? And now we're done. We end while. There's no return on this, but all we want to do is see that that's actually going to be the number of times this thing actually runs. How many times did it run? It ran 3 times. Okay? Did this matter based upon the size of the data set? No, because this wasn't actually pulling off of a data set. Okay, so we didn't really actually need to think about like how long was the data set, anything else like that, because this one wasn't actually running off a data set. It really depended upon the value of count. Okay, and if we were doing some number theory, what you would see is you'd see, well, that's, if I take count divided by 3, and yeah, if I took count divided by 3, that would, or count divided by 2, pardon me, that would tell me how many times I would decrement. All right, so that's my first while loop. Let's go in and let's try some things out. All right, I'm going to kind of give you some instruction, and then I'll have you try some things. So now let's look at an example. So we're going to write an out. This one asks us to write an algorithm pseudocode. What I really want to do is I actually just want to analyze the algorithm pseudocode. I'm not going to worry about the writing of it. It's not something that I really want to do too much of here in this class. It's just not. So we want to imagine we have an input. It's a sequence of numbers. N is greater than or equal to 1. And then n is the length of the sequence. It's going to go a sub 1 through a sub n. That's actually how we read these, a sub 1 through a sub n. And our output is going to be true if the sequence is non-decreasing, and it's going to be false otherwise. Right? So if we have a non-decreasing sequence, we're going to get, true, and otherwise if it's either increasing or if it's decreasing or non-increasing, okay, then we are going to get false. All right. Now, so the algorithm determines whether or not the sequence is non-decreasing. So we have an input. It states our input, okay, and this is how we often see the pseudocode. And then it tells us what our output is. And now what we're going to do is we are going to have to use a for. We're going to use a for loop here because we need to test the whole sequence. Since we are testing the whole sequence, that's why we're going to end up using the for loop, okay? And what we're going to see here is if I'm going to test the whole for loop for 2 to n, okay, the number of computations that I'm going to have to do there is going to be n minus 2 plus 1, which equals n minus 1 computations. Okay? What this is going to do then, and you want to be able to read this and understand what it is, this is going to say I'm going to pick out if a sub I minus 1 is greater than a sub I, we're going to return false. Okay? And basically what's happening here is each and every time I'm going to test, and if the previous value is greater than the one after it, then I'm going to return false. Okay? Eventually, we'll get to the end of the list. Once we get to the end of the list, if we never return false, it's going to return true. So basically what this does is it actually goes in and tests to see whether or not we end up having any kind of, if the previous term is bigger than the one after it, right? Okay, so we start with 2, we look at 1, we see, oh, you know what? A sub 2 is bigger than a sub 1, we're good. Okay, a sub 3 is bigger than a sub 2, or the same size, whatever it is, we're still good. And so what you see here is that this one is going to actually pick out and see if we can find something that's not our quality, right? Or not the quality that we're looking for. And that gives us the return of false. Now, the nice thing about this is that in this case, if let's say, for example, the first two, if we say we have 3, 2, okay, 3, 2, then in this case, what you notice, if this is a sub 1 and this is a sub 2, we actually get a decreasing, we start to decrease, and at that point, we just return false, and we're done. We don't actually have to do anything more. So actually, in this case, this for loop actually defines, our best case would be we'd only have to do this once. Our worst case is we actually end up with something that gives us a true, and we have to go through all n values, or we have to do n minus 1 computations. So let's consider this particular algorithm. We want to find some identical neighbors. Okay, so we've got the inputs a sub 1 through a sub n. It's a sequence of numbers where n is greater than or equal to 1. And we're going to output in true if there are 2 consecutive numbers in the sequence that are the same, and false otherwise. Again, notice that what we're using is a for statement. Okay, and in our for statement, we want to notice again that the worst thing that could happen is that we in fact have no 2 numbers inside of the sequence are actually in fact identical. So we'll get n minus 2 plus 1, which equals n minus 1 computations. Right? That's what happens if none of them are the same. If we now go in, if a sub I minus 1 is equal to a sub I, we'll return true. So you can imagine that if you had a sequence, say for example like 1, 1, 2, 3, 5, 7, that notice that the first 2 values here, a sub I and a sub I minus 1, or a sub 2 and a sub 1 in this case, in fact are identical. Since they're identical, we return true, and then we're done. Okay, we end up returning true. We don't have to go back to the sequence again. So again, as we're reading here, you want to think to yourself, okay, well, what would be the best thing that could happen? Like in this case, the best thing is the first two values are in fact 1. And when I say best case, I mean the fewest number of operations, right? The fewest number of operations is, in this case, if the first two are the same, okay? And what's the worst thing that could happen? None of them are the same, okay? We return a false, and that means that we've got to go through the entire list. All right, so the algorithm, this last algorithm we'll look at has a nested loop. And so you're reading some nested loops, and we'll talk a little bit about how to read these, and then also we'll talk a little bit about their counting. So we've got an algorithm that we want to determine whether or not the sequence has two numbers who add to 0. So what you want to imagine is you want to imagine that you're going to go through and you're going to add up, right, each set of numbers, okay, until you see if any one of them actually equals 0, okay? So let's imagine that we want to start out, we've got a for loop. We're going to start with this for loop, and this is going to get for I equals 1 to n minus 1, okay? So theoretically here, we could in fact run this n minus 1 minus 1 plus 1, so we'll run it n minus 1 times. But then notice, then we're going to go from j equals I plus 1 up to n, okay? So how we read this is like this. Let's say, for example, I'm going to have let's say that n is equal to 10. All right, so we have a sub 1 through a sub 10. Okay, a sub 1, a sub 2, a sub 3, a sub 4, so on and so on and so forth until I hit a sub 10. Now, for I equals 1 to n minus 1, okay, we've got I equals 1 to, in this case, 9. We're going to start there, and so we'll start with a sub 1, just like we did before. All right, we're going to start with that first value, a sub 1, and then next, though, we're going to look for j equals I plus 1 to n. So now that's going to look at we're going to start with a sub 2. So that our i's are going to start with a sub 1, and our j's are going to start with a sub 2. And then what we'll do is we'll see whether or not the two add up to 0. So we'll take a sub 1 plus a sub 2, and that'll equal 0, right? Yes or no? If it's yes, then all we've got to do, we've only had to do that one computation. We've had to go in, we've had to assign, and then add the two together, see in fact that it equals 0, we return true, we're done. Okay? On the other hand, what if a sub 1 plus a sub 2 does not equal 0? Right? Okay, what if we get a no? Then what we're going to do is we're going to stay on a sub 1, and we're going to increment j. J is on the inner loop, right? So j is on the inner loop, so we're going to increment with j, and so you're going to get a sub 1 plus a sub 3. And we're going to see, does that equal 0? Yes or no? Okay, true or false? T or F. Probably better to call it T or F. Okay, let's say it's false, then we're going to do a sub 1 plus a sub 4. That's the next j. So these are all of our j's. The j's here are the a sub 1s through a sub 4s. And let's say we go a sub 1, and we keep doing this until we hit a sub 1 plus a sub 10. And let's say that does not equal 0. We get a false there too. Then what we got to do, we've gone through every single value from I plus 1, right? I plus 1 being 2 to 10. We've done that for every j. Now what we're going to do is we're going to go back. We're going to exit the for, and we're going to that inner for loop. We're going to go to the outer for loop, and we're going to increment I. Now I is going to be 2. Okay, and we're going to do the same thing again. We're just going to do it one fewer time. So we're going to have a sub 2 plus a sub 3. Okay, determine whether or not that equals 0, yes or no. A sub 2 plus a sub 4 equals 0, yes or no, true or false, right? We get a false, let's say, for example. And we'll do this until we hit a sub 2 plus a sub 10, and we'll make a determination as to whether or not that equals 0, true or false. And let's say, for example, it is false, then I'm going to increment again to I equals 3. I've gone through all my j's, 2 through 10, right? Now I've got to go and increment for my i's. For my i's on this for loop, and we're going to, like I said, we're going to talk about this a bit more. My i's are, once again, I'm going to look at this, and this is going to go 1, right, n minus 1 minus 1 plus 1, which equals n minus 1 times. So I've got n minus 1 i's. My j's, on the other hand, it's a little bit more difficult. You're going to see this written like this. You're going to see it as n minus I plus 1, and then again, plus 1. Okay? So this is going to be n minus I. Okay, that's basically going to be the value that we get for our j. How many times am I going to run that j? I'm going to run that j n minus 1 times. So let's take our example here. One thing to notice here, and it's kind of tricky to think about, is that I actually changes. Remember that the I that we get, it's going to change each and every time. Okay? It's going to change each and every time because I changes. As we increment I, right, I is going to change, and so consequently we get a bigger and bigger and bigger number. So what's going to end up happening is I'm going to get n minus 1. That's the first time when I had I equal to 1. But then notice that when I equals 2, I'm only going to go from 3 to 10, and that's 8 times. Okay? So that's going to be n minus 1 plus n minus 2. The third time is going to be n minus 3. And then the fourth time is going to be n minus 4. And then we're going to keep going with this until we finally get down to just the one computation. That is a sub n plus a sub n minus 1. That's the last one I've got to do. Okay? And so what we've got here, what you'll notice is that we've got n, all right? We've got the sum, I equals 1 up to n minus 1 of, essentially we call it k, okay? And if you know anything about this, it's going to be n minus 1 plus 1 times n minus 1 divided by 2. And this is it's a formula for summations. And so essentially what we get is we get n squared minus n divided by 2 is going to be the number of computations that you've got to do. Okay? So this is what we call the biggest number of computations you have to do. The biggest number of computations. Let's not worry too much about this. We're going to talk about this. We're going to simplify it quite a lot when we talk about worst case time complexity. But essentially what you'll notice is that because I've got this nested loop, all right, what ended up happening is the number of computations that I had to do really increased by quite a lot, by a factor of 2 in this case. So this kind of completes out like the reading of our algorithms. I'm going to put up more videos on how to read algorithms and how to read pseudocode. It just takes a little bit of practice. We're going to practice a lot when we talk about worst case time complexity. We'll look at more algorithms. What I want you to do is I really want you to kind of like go in here and get comfortable with kind of reading the very basic for and while loops and start to think through, well, how many operations am I going to be doing if I look at a particular piece of code?